The line is rising faster than anyone expected in 2026. This update cuts straight through the nonsense to reveal the most jaw-dropping construction milestones and the relentless 2026 timeline that Saudi Arabia has adopted for the project. We'll uncover exactly how far the world's most ambitious linear city has come and why this year's progress changes everything you thought you knew about the project. As of early 2026, construction at the Line megaproject in Saudi Arabia is centered on the development of its initial 2.4-kilometer pilot phase. This segment represents the first physically realized portion of a planned linear city that, in its full scope, is intended to span 170 kilometers in length, 200 meters in width, and 500 meters in height. The current phase is not focused on visual landmarks or architectural finishes, but on essential groundwork, specifically deep foundation systems that will support the superstructure in later stages. The dominant construction activity at this stage is piling. This process involves drilling and installing deep cylindrical foundations made of reinforced concrete. These piles are necessary to anchor the line's structural cores to stable ground layers, especially given the immense weight and vertical load that the future city will impose. Construction teams are using rotary drilling rigs and continuous flight auger systems to bore into the desert soil, often reaching depths of 40 to 50 meters. The length, diameter, and spacing of the piles vary depending on the location and the engineering requirements of each segment. By January 2026, thousands of piles have been installed across the core section of the 2.4-kilometer site. These piles are grouped in dense arrays, typically beneath the locations where vertical cores will rise. Each vertical core will eventually support structural floors, internal transit systems, and integrated service zones, so precision in pile alignment is critical. Surveyors are present at every stage to ensure tolerances are maintained to engineering specifications. Reinforcement cages made of high-grade steel are pre-assembled nearby in on-site fabrication zones. These cages are lowered into the drilled shafts before concrete is poured in a continuous sequence. Concrete is mixed and delivered using mobile batching plants, many of which have been temporarily constructed on-site to ensure proximity and consistency in material delivery. This helps control hydration time and maintain quality across the large-scale pour operations. The logistical setup to support this work is extensive. Access roads, staging areas, crane pads, and equipment storage zones have been built across the site. Dedicated areas are allocated for steel delivery, formwork preparation, and curing stations for concrete samples. Each working zone is served by a fleet of transport vehicles, including pump trucks, mixers, loaders, and flatbeds. Temporary worker accommodations are located adjacent to the construction site. These include modular housing, food service areas, safety offices, and logistical control centers. At peak capacity, workforce numbers for the piling phase alone have reached into the several thousands, including civil engineers, geotechnical teams, machine operators, and laborers. Work is scheduled in staggered shifts to avoid heat peaks during daylight hours and to maintain 24-hour operation across the site's critical piling zones. Alongside piling, excavation for utilities and service corridors is underway. Trenches are being cut parallel to the structural footprint to house future electrical conduits, wastewater piping, and cooling infrastructure. These trenches are between 4 to 8 meters deep, depending on their purpose. Prefabricated conduits and reinforced concrete segments are being installed in these excavations, many of which will remain accessible for maintenance once the superstructure is built overhead. Survey and soil stabilization work is ongoing beyond the 2.4-kilometer pilot zone. Teams are using ground-penetrating radar, core sampling rigs, and vibration sensors to assess subgrade conditions along the broader planned alignment of the line. The aim is to prepare adjacent land for future construction stages by identifying areas of weakness or instability in advance. As of the first quarter of 2026, the entire construction operation is supported by a central site coordination hub. This includes digital project management systems that track every pile installation, every material delivery, and every inspection in real time. Drones and LiDAR scanners are deployed weekly to generate up-to-date site models, which are fed into a central BIM platform. This allows all contractors and subcontractors to coordinate changes, flag issues, and update progress data from a unified source. Material logistics are tightly controlled. Steel rebar, formwork components, and mechanical parts are imported through nearby ports, then transported via overland routes to a series of internal storage yards within Eniome's logistics corridor. Inventory is scanned and monitored through RFID and GPS-linked tracking systems to avoid delays and minimize losses. Because the scale of the line demands long-term continuity, the early stages of construction also include investment in permanent support infrastructure. These include power substations, access tunnels, and water distribution nodes that will serve not just the construction site, but the future urban systems of the line itself. In parallel to the piling operations, groundwork is being laid for temporary substations to provide electricity to cranes, batching plants, and tunnel boring machines once the underground systems begin. Environmental mitigation procedures are in place. Dust suppression systems have been deployed, with water trucks and fixed spraying systems keeping particulate matter under control. Monitoring stations log air quality, noise levels, and soil movement across dozens of checkpoints, feeding data to Eniome's regulatory and oversight bodies. Part of the site's ongoing work includes constructing sediment basins and drainage controls to manage flash flooding during rare desert rain events. At this stage of construction, no structural elements are visible above ground beyond crane masts, equipment platforms, and temporary scaffolding. The visual impression of the line in early 2026 is defined by wide excavation zones, drilled pile caps, and grids of reinforcement cages awaiting concrete pours. Despite the massive investment and scale of activity, the current phase is not yet architectural. Rather, it is purely structural and preparatory. The goal for the first half of 2026 is to complete all foundational works within the 2.4-kilometer pilot segment. Once the last pile is driven and all ground-level systems are installed and tested, the site will transition into superstructure assembly. That phase, projected to begin in mid-2026, will include the installation of vertical core frameworks and the first deck slabs that will make up the internal layout of the line's cross-sectional modules. This phase also marks a checkpoint in construction strategy. Engineers and planners will use the data collected during the first few months of piling and trenching to evaluate the accuracy of early forecasts, material performance, and workflow efficiency. Any issues that arise, such as subsurface anomalies, delays in material delivery, or mismatches in system integration, will be used to adjust methodologies for the next construction zones. By the end of the first quarter of 2026, the bulk of piling operations across the 2.4-kilometer pilot segment had reached completion. Nearly every core location designated in the master plan had been stabilized with dense clusters of deep concrete piles, many reinforced with steel cages and anchored into bedrock. As each group of piles was completed, capping beams and pile heads were poured and leveled, forming flat zones where superstructure elements would be installed next. With this stage wrapping up, attention shifted to preparing the site for vertical construction. The transition began with the installation of starter bars, protruding steel reinforcements emerging from pile caps designed to connect the substructure directly to the vertical cores that would rise above. Survey crews worked around the clock to ensure that tolerances between pile caps and future core positions were within millimeter precision. Each misalignment risked compounding errors as construction moved upward. At the same time, site logistics were reconfigured. Heavy piling rigs were demobilized, making room for tower crane bases steel staging areas, and temporary platforms that would support formwork and rebar assembly. The shift in operations also required a new layout for internal roads and access paths. Routes that once carried in concrete trucks and drilling equipment were adjusted to allow for steel deliveries, pre-assembled formwork systems, and mobile crane positioning. By mid-March 2026, the first signs of vertical progress became visible at the heart of the pilot zone. Initial work focused on a cluster of structural cores designed to anchor a key section of the line's internal transportation system. These cores, roughly 10 meters by 10 meters in cross-section, are cast-in-place, reinforced concrete structures designed to house elevator shafts, mechanical risers, and future high-speed rail conduits. Each core is being constructed in sequence using a climbing formwork system. Rebar is laid by hand at each level, followed by concrete pours that are carefully timed to allow curing and form removal before the next lift is positioned. A typical core advances at a rate of 1 to 2 meters per day, depending on site conditions and workforce availability. At any given time, multiple cores are at different stages of ascent across the 2.4 kilometers zone. Once a core reaches its designed floor connection height, roughly every 10 to 12 meters, preparation begins for the installation of the first horizontal structural elements. These include steel outrigger beams and prefabricated deck segments, which will span the gaps between cores to form the base of the line's stacked internal layout. Steel components are being fabricated off-site at regional manufacturing yards and transported to NEOM's logistics hubs by road. Upon arrival, they are offloaded, inspected, and staged in holding areas until the receiving core pairs are ready. The steel is pre-drilled and treated with corrosion-resistant coatings due to the project's proximity to coastal conditions and the long-term exposure requirements. Lifting operations are executed by a combination of crawler cranes and temporary gantry setups, depending on the beam length and weight. Each beam is positioned with GPS-guided accuracy and temporarily braced until permanent welding and bolting can take place. Crews working at height operate in tandem with ground-level rigging teams, following detailed lift plans approved by site safety and engineering leads. As of April 2026, the first horizontal segments have been successfully connected between multiple core pairs. These initial spans form what will eventually become transit corridors, pedestrian walkways, and mechanical floors. Additional deck slabs, constructed from precast planks and poured-in-place topping layers, will be installed above and below to create multiple usable levels within each section. While vertical progress continues, secondary systems are also being integrated concurrently. Embedded conduits for electrical, HVAC, and data systems are being installed into formwork before each core pour. This pre-embedding process ensures minimal retrofitting later, reducing both cost and complexity as the project scales. Crews responsible for mechanical, electrical, and plumbing integration work alongside structural teams during early-stage core construction to align shaft openings and bracket placement. At the perimeter of the 2.4 kilometer zone, civil works teams continue to expand utility trenches and connection nodes that will link the pilot segment to broader NEOM infrastructure. These include main feeder lines for power, chilled water, and fiber optic systems that are being routed in parallel with the building envelope. Where necessary, deep concrete channels are cast in sections to carry future automated freight systems and utility robots, key components of the line's long-term operations model. The construction site is now operating under two coordinated zones: active vertical construction in the central segment and groundwork and utility preparation extending outward in both directions. The sequencing allows for continuous material flow and task specialization, with crews assigned to specific operation clusters rather than rotating between unrelated tasks. To support the growing complexity, the site's digital coordination systems have been expanded. RFID tags on every major structural element are scanned and logged into the site-wide BIM system, which maps construction status in real time. Drones are deployed twice daily to conduct visual inspections, photogrammetry scans, and material stockpile assessments, which are then compared with progress models to track actual versus planned delivery rates. Safety remains a primary focus as vertical construction intensifies. With more workers operating at height, the number of harnessed personnel has increased significantly. Fall arrest systems, perimeter netting, and stage safety platforms have been installed across every working face. Toolbox talks and safety briefings are held at the start of each shift, and real-time alerts are issued across wearable devices to warn of wind gusts or high crane loads. As May approaches, planners anticipate an acceleration in vertical work rates. The number of active cores under construction is expected to double by early summer, and steel connection work will ramp up accordingly. By mid-year, the first fully enclosed structural frames, comprising cores, horizontal connections, and multiple floor levels, are scheduled for partial handover to interior fit-out teams. Even at this stage, progress remains heavily dependent on logistical throughput. Materials procurement, customs clearance, and on-site delivery all affect construction momentum. In response, the NEOM Logistics Division has introduced staggered delivery slots for high-priority components, allowing smoother crane scheduling and minimizing downtime caused by material congestion. Looking slightly ahead, the next major milestone will be the installation of the first facade panels, though this is not scheduled to begin until the second half of 2026. These mirrored glass elements are being produced under controlled conditions to meet both structural and energy efficiency standards, and will require precision mounting brackets already embedded in the concrete cores during the current phase. By mid-2026, the construction of the line's first 2.4-kilometer pilot segment has fully transitioned into an active superstructure phase. The structural cores that began rising in early spring have reached planned elevations in several clusters, and these cores are now linked horizontally by primary steel outriggers and deck systems. The worksite reflects a complex, multi-layered build, with vertical and horizontal structural elements being assembled concurrently across dozens of locations. As vertical construction progresses, the cranes on site have diversified in function. In the early months of this year, the primary role of cranes was to support the lifting of rebar cages and concrete pumps during core construction. By June and July, these cranes are lifting increasingly large steel deck segments, precast concrete slabs, and modular mechanical elements into place. Tower cranes now occupy fixed bases throughout the pilot segment, providing structured hoist capability at designated cells of construction activity. In these months, the decking system, consisting of horizontal beams and slabs spanning between reinforced concrete cores, has begun to define the internal geometry of the line. These horizontal elements form the skeletal structural floors that will ultimately accommodate internal transit lines, residential levels, commercial zones, and mechanical infrastructure. Each segment of deck is installed with exacting precision, requiring detailed alignment checks and real-time adjustments to meet design tolerances. Connections are secured with high-strength bolts and complemented by on-site welding where required. Alongside this visible progress, significant work is underway on below-grade transit tunnels that will carry the line's automated mobility systems. These tunnels run parallel to the superstructure footprint, but at a lower depth, typically 15 to 25 meters below the future ground plane. Boring crews operate tunnel boring machines imported specifically for this project's unique profile, and segments of tunnel are continuously lined with precast concrete rings that ensure stability and waterproofing. In several zones, these tunnels intersect with the vertical cores being constructed above. This has required careful staging and sequencing, with civil and structural teams collaborating to create reinforced spines that accommodate both overlying decks and underlying transit conduits. At these core-to-tunnel junctions, engineers install transition frames, specialized steel and concrete components designed to absorb differential movement and maintain structural continuity across different systems. Equipment for transit systems, such as guideway rails and cable trays, is being staged along freshly bored tunnel segments. Although full installation of the transit system is scheduled for later phases, early integration points are being prepared now to allow faster installation once superstructure framing reaches operational levels. This preparatory work includes placement of anchor points for guide rails, pathway lighting conduits, emergency egress markers, and initial communications fiber paths. The integration of building systems has begun in earnest as structural elements reach stability. Mechanical, electrical, and plumbing subcontractors are installing embedded utility conduits, risers, and anchor boxes during the deck installation process. This method, known as concurrent MEP integration, minimizes rework, reduces conflicts between trades, and streamlines future phases of fit-out. Electrical conduits, for example, are laid into deck formwork prior to concrete pouring, while HVAC duct supports are bolted into place using pre-embedded inserts. Project planners have reported that power distribution nodes are now being constructed across multiple locations within the pilot zone. These nodes consist of medium voltage switchgear, distribution buses, and transformer banks designed to feed both construction power and future operational loads. To support 24-hour construction demands, temporary power substations have been operational since early 2026, but the new permanent nodes will eventually replace them as the backbone of the line's electrical network. Water and wastewater systems are also being installed in alignment with the superstructure. Large diameter water mains have been laid in service trenches adjacent to structural grids, and waste piping is being routed vertically through core shafts to connect to treatment zones outside the 2.4 km segment. These systems are sized based on projected occupancy loads and redundancy requirements, with capacity for future expansion as additional modules are built. Environmental control systems, such as stormwater collection, ground cooling loops, and dust mitigation networks, continue to be updated in tandem with structure. As more of the pilot segment reaches elevation, runoff management becomes critical. This requires properly graded surfaces, catch basins, and drainage piping capable of directing water away from deck edges. Grading teams use laser-guided leveling systems and GPS control points to ensure proper pitch and alignment as the decks rise. Workforce coordination has become increasingly complex as the number of active trades grows. Structural crews, MEP installers, tunnel workers, and logistics personnel now share overlapping work zones. Project managers rely on a centralized building information modeling system to sequence tasks, manage clashes, and allocate crews. Daily coordination meetings review progress, identify bottlenecks, and adjust upcoming work windows to maximize productivity while maintaining safety. On the quality management front, inspectors conduct regular checks on structural welds, concrete strength samples, and steel tolerances. Non-destructive testing techniques such as ultrasonic inspection and magnetic particle scanning are deployed for critical connections, particularly in areas where structural loads are highest. Concrete cores are subjected to compression testing at off-site labs, ensuring that mixed designs meet performance targets before the next phase of floors is constructed. By late summer 2026, progress markers, such as the number of completed deck segments and operational tunnel rings, become standard metrics reported in weekly construction updates. Engineers tally the number of core sections that have reached designated floor heights and assess how quickly adjoining decks can be installed. Procurement teams maintain aggressive supply schedules for steel alloys, precast components, and specialty equipment like tunnel lining segments and electrical switchgear. Environmental monitoring remains operational across the site. Air quality stations log particulate levels and humidity, while acoustic monitors ensure compliance with construction noise limits. Water usage is tracked closely due to the desert environment, and recycling systems collect rinsate water from drilling and concrete pumping for reuse in dust suppression and initial curing processes. Worker safety programs continue to expand as activity intensifies at height. New safety platforms, engineered fall arrest systems, and elevated walkways have been installed to allow safe movement between core towers and deck assemblies. Safety briefings cover specific risks associated with elevated deck work, heavy lifting, and tunnel excavation nearby. As 2026 enters its final quarter, the construction plan anticipates several key transitions. Superstructure assembly is expected to reach a continuous band of linked decks over a majority of the pilot zone, enabling interior access points to be established for fit-out preparation. Transit tunnel excavation is projected to complete its next milestone of connecting 3 major logistics nodes beneath the central portion of the 2.4 km corridor. Electrical distribution frameworks will be energized sectionally, allowing on-site systems such as lighting, MEP control centers, and workshop power to migrate away from temporary generators. Another major area of focus is temporary weather protection for open structure areas. As deck spans grow and more work is performed above ground, modular tarpaulin systems and retractable roofing sections are installed to protect internal work zones from the elements. These protective systems allow fit-out crews to begin work even before the full building envelope is completed, improving overall schedule resilience. Late 2026 will also see the first internal coordination walkthroughs, guided site inspections where architects, engineers, and MEP leads review installed systems, validate tolerances, and begin planning tie-ins for future mechanical equipment rooms. These walkthroughs are critical transition points, marking the shift from structural contractor oversight to integrated systems coordination in 2027. As the final quarter of 2026 progresses, the construction site at the line continues to evolve from a heavy structural work zone into a multi-layered, interconnected urban shell. The focus across the 2.4 kilometer pilot segment has shifted towards systems integration, internal layout development, and preparation for both facade installation and future occupation phases. By October, most structural cores within the pilot zone have reached their intended heights. The horizontal deck spans linking them are over 75% complete, with the remaining gaps in installation concentrated in areas requiring custom connection joints or embedded infrastructure zones. Workers are installing the final levels of decking, including rooftop mechanical platforms and future solar integration spaces. These decks are not monolithic slabs. Each level serves a specific urban function: transit movement, pedestrian circulation, residential floors, commercial corridors, or technical infrastructure. Staircases and core risers between decks are now being fitted with access platforms and frame supports for future elevators and escalators. Transit-related decks include anchor points for high-speed guideways and smart mobility paths. Inside the structure, the first permanent mechanical rooms are under active build-out. Mechanical, electrical, and plumbing teams are installing electrical switchgear cabinets, water pumps, HVAC air handling units, and fire safety systems. The project is still in early phases of systems activation, but all permanent utilities are now routed into the segment, with service corridors fully enclosed and protected. One of the most anticipated transitions is now underway: the beginning of facade preparation. Steel brackets and anchor points embedded in the concrete structure months earlier are being rechecked for precision. From these points, the external mirror finish panels of the line's reflective facade will be hung. The panels are fabricated off-site, shipped in pre-sequenced deliveries, and stored in climate-controlled conditions until installation begins. As of November 2026, the first rows of facade mounts are in place, but full-scale cladding will begin in early 2027. Before that, mock-up installations are underway within a dedicated test zone at the edge of the pilot site. These mock-ups test how the facade handles thermal expansion, wind loads, and visual consistency across panels, all critical for a 500-meter tall mirrored wall stretching over many kilometers. In parallel, mock-up interiors are being constructed on the upper floors of completed deck sections. These test units are not for public display, but are used by engineers and building systems teams to simulate ventilation, lighting, and occupancy conditions. Data from these rooms helps refine the approach for the larger interior fit-out scheduled for the following year. By December, system calibration and soft commissioning begins for certain sections of the pilot. Electrical distribution networks are energized, water pressure tests are conducted, and communication nodes are activated to verify connectivity across the site's internal network. Small teams begin dry running building management software, which will eventually automate energy flow, environmental controls, and internal transport guidance. Outside the structure, final grading and paving is underway across the pilot site's access roads and logistics staging zones. These temporary roads are being upgraded to permanent utility corridors or transformed into landscaped outer zones. Some early-stage landscaping, mostly soil stabilization and heat-tolerant vegetation, is installed to begin modeling the line's future microclimate management approach. Workforce density at the site begins to peak as the year closes, with construction headcounts increasing to over 40,000 across all shifts. Specialized trades, cladding teams, automation system technicians, modular interior installers are brought in to prepare for 2027's accelerated build-out. Looking ahead into 2027, the primary objectives will be facade completion, full interior fit-out, activation of core mobility systems, and the initial onboarding of operational personnel. Engineers project that if the current pace continues uninterrupted, the pilot segment will be partially habitable by late 2027, with first phase occupancy occurring in tightly controlled stages. Beyond the pilot, planning for adjacent segments is progressing. Survey teams and geotechnical units are already active beyond the 2.4 kilometer zone, and early site prep, including road extensions and site fencing, is expected to begin in the first quarter of 2027. These follow-on modules will use the same structural system and are expected to be built more quickly thanks to the lessons and data gathered from the 2026 effort.